Hello everyone. Today I'll be doing a quick rundown of the UML search engine project. We will start by going through the quick start that can be found in the README of the repository. Through the process, we will export the model as JSON and followed by building the Elasticsearch index uh, and then running the index and along with a built element rank index and using both those indices to search for certain queries. And then we will go over presenting the results of those queries in the form of A/B or multivariate tests in the tool that users are most often are used to seeing search results in. So let's get started. Going to the top, keep in mind that this first step of exporting the model as JSON is completely optional. In fact, the pre-export for the TMT or 30-meter telescope open source model is provided in this repository in the resources folder as a zip. So if you want to go and skip this, which I recommend as it requires installing a commercial tool and running a macro in it, you could simply unzip the contents of that, uh, unzip that zip and replace wherever CSM JSON is mentioned in the rest of this quick start with whatever repository you chose to extract it to. But for the sake of example, I'm going to go ahead and show what one would need to do if they wanted to do this. So the dependencies are listed here. So first we'll need Cameo Systems Modeler. You can download this from the vendor's website. So for our purposes, all you'll need is the trial version. All that means is that you won't be able to save elements or save models that are above a certain size. But for our purposes, we'll be only using the model in read only. So we won't actually need to save it for to do this demo. So go ahead. You will have to register an account here as well. So I already have one. I'll go ahead and log in to show you what the download page looks like. So that's what the download page looks like. It's the Cameo Systems Modeler that we are interested in. So this will come pre-bundled with all the plugins we need. We're going to change the version to 18.5 feature release because that was the version tested with. Hit next there. And here are all the downloads. So the download that I recommend is the no install. This will work on any platform and just provide a zip that you can download or an extract somewhere. And wherever you extract it will be the $CSM variable that we see later on. So I already have this downloaded, so I'm not going to re-download it. But you'll also notice here that the key has been sent to my email address. We will need this. Again, I already have this downloaded as well. So to reiterate, the no install zip and the license file that it will be in your email. Next, we will have to go to the model development kit is an open source plugin for the Cameo simulation or systems modeler software. You can find it on Bintray. So we'll be using the libraries in here. So this is the download. So I just went to the website and different versions. The version that I'm interested in is 3.2.2. And since that, as of recording, that's the latest version. So it's on the downloads page. If later on it is not the latest version, you can go into versions here and find the one you're interested in. And then it'll be on the bottom there. Again, I have this downloaded as well already. Next, we will want the TMT, again, 30-meter telescope SysML model. It's the largest open source UML/SysML model that I know of at least. So we will be using that as, it's also in active development, so there are engineers who can provide their feedback on the results of this application to help evaluate the effectiveness of the different search algorithms. So I'm at the repository. So in the README, I specified specifically what commit we are interested in. So if you want to reproduce the test exactly as I am running it, then you can go to the commit and find the right one, and so uh, and let's see, browse files. There we go. So now we're in the tree for that specific commit. I can go ahead and download it. Download zip would be the easiest thing, or you could check it out either way. And again, I have that already. Moving on to the initialization steps. Once we've downloaded all those dependencies, we'll start with the Cameo Systems Modeler zip file, and we'll go ahead and extract it. So extract it right here. Next, we will extract the TMT zip. Okay, and then we will, once it finishes extracting, we'll execute CSM bin and then the CSM executable. It's right there, the .exe. Run here. It'll ask me to import config sometimes. I'm gonna choose not to. Use default. Licensing agreement, yeah, sure. And then I will want to select license key files. So we'll go to our downloaded file. And this is, again, the one we received in our email when we downloaded. Go and open that. Evaluation, sure. While that's opening up, select license. Next, we'll have to install the plugin that we downloaded. That will help with serializing the model elements to JSON. So to do that, cool. We'll go to help and then resource, register later. At help, resource plugin manager. And then at the bottom of this page is import. From import, we'll go back here, go down to our downloads, and choose the MDK plugin zip. So it'll say successfully installed, but it'll only take effect after I restart Cameo Systems Modeler. Okay, so go ahead and close out of that. Exit out of Cameo Systems Modeler. And the initialization for this first step is done. Now, we're going to have to re-execute. Remember, the restart was important because the install of the plugin does not take place until the restart happens. So there we go. While that's starting up, the next step will be opening up the project we're interested in. So in the directory we extracted the TMT Git repository into, there will be a file called tmtmdzip. That's the one we'll want to open. Agree. Workspace. So there we go. Open up that folder, and then tmtmdzip. Go and open that. So it'll say I can't find something, and this we can say no. It's not important for this. While that's opening up. So the next step will be to create a macro, and we're going to use this macro to extract the model elements as JSON. So for that, the macro that we want, it can be found in the repository for the UML search engine repository. So I'm going to go ahead and extract that. And we can find that under resources, and it's the dump.json.groovy file. So going back to this, now that it's opened, I'm going to cancel. This one's also not important. So here's the information about the demo version. We understand. We won't be able to save, and that is fine. We will not need to. So under tools, macros, and then create macro, we'll open up this pop-up. We'll want to change the macro language from the default to Groovy. We'll want to come back here, and I'll just open this with any text editor. Oh, maybe not this one, if it doesn't do line. Oh, it is. That's fine. So there, go ahead and copy that. So, and now I will run it. So this is blocking the swing thread, so it'll look like the application's frozen, but the files are actually being generated right now. Where we can find that is in the directory where Cameo Systems Modeler was created. There will be a new folder called JSON, and inside there will be a new JSON file for every element in the model. So there we go. We see that it's being created, still running. So while that runs, we're going to take a look at the next step. So yeah, that was once the macro finishes, that will be completion of part one. So we have the output of step one is, or part one is a JSON file for each of the elements in the model, and these are what will be used to populate the Elasticsearch index. So for the next step, we'll want JDK8 for I'm running with 8U151. It's the latest as of now. There's the download link. Standard Elasticsearch. There's the download link. 611 is what I'm running. So I already have these downloaded here, and I have the JDK installed. Elasticsearch, I'll do a fresh extract of that. So fresh install. So this is an optional step, but while populating the this model, since it is a relatively large one, 139,000 elements, I found that it helped to increase the allocated memory. So I'm going to go ahead into config, and then JVM options. Going to Notepad is not cooperating with me, so I'm going to open it here. And it defaults to 1 gig. I'm going to go ahead and bump that up to 8 since I'm not. So I don't actually know the minimum requirements, so as much as you can allocate for this would be better. So that's ready to run. We'll see if this is done. Oh, it's still running. So I actually already have the, or I guess I'll go ahead and show you the other way of just using the ones that are included under the resources here. That'll probably be faster. So the TMT JSON zip file has what you're interested in. So I'm going to go and extract the files, and yeah, anywhere is fine, really. Oh, and this is done now. So we can go ahead and close out of this now. No need to save, we have it already. So it'll tell you that it's finished executing. And we'll just take a quick look over here. There we go. All the JSON representation for all the elements. So moving on to using those. So we've finished the dependencies, the initialization, and we will go ahead and run Elasticsearch with those 8 gigs that we allocated. So I went to the bin folder in the Elasticsearch directory, and since I'm on Windows, I executed the batch file. And there we go. That should be running. So I'm not changing for the demo. I haven't changed the defaults. No password protected. Or rather, the indices are not password protected. Just a default install of Elasticsearch. Moving on. So now it's time to build the UML search engine project itself. So going back to the checked out repository, or the zip that we downloaded of the repository, I can go ahead and extract that. Oh, I already have extracted that. That works. So in here, I'm going to go ahead and open up a command prompt. So I'm using command prompt since everyone has it, but this project is a Gradle project. So if you prefer to use your favorite IDE like IntelliJ or Eclipse, both of them have excellent support for Gradle projects. You can do it that way. So next we're going to change directory into the one we checked out the repository into, or the one we extracted the zip of the repository into. So for me, that's this directory, and then I'm going to run the Gradle wrapper and execute the task shadow jar. So what this will do is it'll build a jar that includes all the dependencies as well as the compiled source code. So it'll make executing from the command line much easier. There'll only be one thing in the class path. So next, we want to go ahead and execute. And what this is going to do is it's going to build or initialize the Elasticsearch index. So in order to do that, we're going to add our newly created jar file, the shadow jar, to the class path. There we go. And then we're going to run the CLI class, and we're going to specify the directory, and this directory is going to be the one where we have all the JSON files that we freshly extracted for our case, or for the case where we're using the pre-exported JSON files from the repository. Just replace the path with wherever you extracted that TNT JSON zip file. So here we go. Everything looks good. Oh, I gotta restart the Elasticsearch index, or Elasticsearch instance. So I'm gonna make sure that the config looks good. Perfect. Give it just a second to start up. There we go, started. Switching back here. And there we go, it's gonna start creating documents for each of these elements. So when it finishes, we'll be able to move on to the next step. So I'm gonna go ahead and skip ahead with some Hollywood magic. And there we have it, guys. The Elasticsearch index has been initialized with all of the elements from the model. So that completes part 2 of building the Elasticsearch index. Part 3 will be building the element rank index and searching for query terms. So the way this one will work is that you'll specify an output directory, and if in that output directory, if a cache doesn't exist, for example, the first time it will not, it will build a element rank index and iterate on the calculations until it converges. And then in future runs, it will use that index that will be stored in that directory to do further queries. So for this part, there are no additional dependencies besides completing or having the dependencies in part 2, and no additional initialization steps except for those in part 2. So it's a matter of running another command line class. So again, we're going to go to the directory that we have this in, and then inside of it, the build libs, and then the shadow jar we built, and then the class for this is that, and we'll choose a directory. Let's make a new one so it'll be easy to see what's happening. Call this element rank. So I'm gonna go and set that as the output directory, and then I can, if I just submit that, it'll only build the index. But let's say I also want to do some queries. So for this, I'll go ahead and use the example queries. These examples were gone from a systems engineer on the TMT team as ones that they would be interested in evaluating the relevance of. Just double checking here, everything should be good. Looks like I'd forgotten a quote after --dir. Again, starting from the top, we are adding the shadow jar to the class path, running the CLI class query indices with the directory set to the new one we just created, and a number of queries after it. Go and run that. So you can see that it's indexing all of the elements again. So this will take a while. But it's once it does this, it will go on to the element rank calculations, and after that, it will iterate through our query terms and generate the output for those. So we will be back in just a sec. As it finishes up indexing here, you'll notice that it starts running the page rank calculations. It iterates until it converges upon a number. That number right now is set to 0.1% of the delta from the previous value. That can be adjusted in the code. And then it iterates through the queries that we provided. And from each query, it asks Elasticsearch for the number of results. So for example, for pupil registration, there are 291 hits that Elasticsearch returns. And then it applies or it adds the element rank score to it as well, normalizes the element rank and Elasticsearch scores, and then generates a result file that orders the hits by Elasticsearch score, by element rank score, and also by a geometric mean of the normalized scores for both of those, which in the JSON file is called combined. It also generates a Groovy macro file that can be run in Cameo Systems Modeler that will display the top 100 results of 100 or less if there are less hits. in the tool that the systems engineer would be familiar with, and well, multiple search results, one for each type of sorting. And the idea is that the systems engineer will be able to evaluate the hits that are between what the tool natively provides, as well as the different search algorithms that we've implemented here, and provide feedback on the relevance of each, and this can be used to evaluate the effectiveness of the different algorithms. So let's go ahead and take a look at what it output. So in the element rank folder, there is an element rank index stored as a JSON file. So in the next, if I were to re-execute this with, say, different query terms, it would reuse this file, so it wouldn't have to do the initialization that it did this time. Additionally, for each, we talked about the hits file that are sorted in different ways. So if we look at one of the smaller ones here, opens, so we'll see that it's a JSON object with keys. So the keys are ES, and then for the Elasticsearch sorting, as they're received, ER for element rank sorting, and combined for the geometric mean between the normalized scores for both of those. And in the, so these are all the fields that represent the element. But at the bottom is added the underscore ES score, underscore ES score normalized, ER score normalized, and the combined score normalized. So these can be used to evaluate why it got the rank. So for example, we may be interested in how this one is, the combined is so high. Well, it's because the ER score is the max that it can be, and the ES score is nearly the max it can be, so high geometric mean as well of those. So in this particular case, it means that both algorithms returned a similar value. So this can be used to backtrace the Groovy file. So if we look at, let me double check what we opened. We opened acquire lock. So if we looked at the test file here, we intend to use for evaluation. The JSON is put here and labeled A, B, C. And in it is an array of the top 100 IDs sorted in the order of the algorithm. So here's A, here's B, here's C. So the user can use these designations to talk about the results, the relevance, which one they liked best, information like that. So we plan to use this for some A/B testing, some multivariate testing. So this is the file that we would send to the systems engineer. So for this one, let's go ahead and check out what this would look like. So for comparison, what we'll first do is we'll use the native search of the application. So if we were to go to edit, find, we could do something. So this is the search window. So in this case, I'm interested in acquire lock. So I can search in just the names, or I can search in all text. And well, we'll get this might be. Nope. So here are the options. I'm gonna go ahead and do that. Looks good to me. So let's go ahead and find. It opens a new tab here with search results. Oh, did not match any items. Well, there you go. Did not match. I will show another. Well, see, it's looking for an exact match. So that just goes back to the problem statement at the beginning, where you know we're looking to interrogate our model. We may not know exactly what to search for, so it didn't find any elements that had acquire lock exactly in it because there are none. but those are two keywords that we're interested in. If we were to do another example, another query term that we were interested in was APS, which is the name of a system in the 30-meter telescope. What I would do, and close the old search results here. We see that it's finding plenty of elements, but it is not applying any sort of sorting to them. It's just iterating through all the elements in the model and finding anything that matches. So, it seems to be alphabetical, but then it breaks that pattern. So it seems to be, see, it's A's down here, D's up here. So it seems to be just the order in which the elements are iterated upon. So these are all the results. Now, with APS, we do see a lot of related elements, but there's no way to know of the one we're interested in. So say the user were interested in the package that contains everything related to the APS. Well, unfortunately, we wouldn't be able to find that very easily because of how popular the term is. So we can see some of the packages that may be of interest to us all the way down here, but as someone interrogating the model with little knowledge of where things are, this may not help one very much. Anyway, we'll see in the next search that there is in fact certain elements that we're looking for the test file. There are certain elements that are likely more related to or more relevant to what the user is looking for. So tools, macros, create macro, change the language here to Groovy, and we're going to copy paste our test file. And when we run this, and run it and close it, no need to save, we'll see that 3 more windows pop up here, and these represent the search results of A, B, and C. So we'll notice here, this is the Elasticsearch one, I believe. So we'll notice that, actually, I mean, they're randomized, so we intentionally don't know. I believe this is the Elasticsearch one. So we'll notice that, applicability, look, it's up there because there is a match with exactly APS. So Elasticsearch using TF-IDF matches things that are very similar to the search term. While on the other hand, well, from here it's indistinguishable, but one of this is the element rank sorting of the Elasticsearch hits, and the other is a combined score. But both of them, you'll see, actually is quite different from the Elasticsearch results because it is prioritizing elements that are highly interconnected in the model. So these are elements that are more likely to be what the user is interested in finding. So if I were to search APS, I would expect to find the package that, I may expect to find the package that contains everything related to the APS. If we select this in the containment tree, we'll notice that, yeah, there's the requirements for the system. That's definitely interesting. If we go up here, well, here we have the use cases for that system, DDD, etc. So preliminary results shows that by already the results from Elasticsearch are an improvement from the native search. Just by applying some sorting, we'll see the package has already made it up here. But by applying element rank on top of that, seemingly on first impressions, we are getting elements that are more related or perhaps more interesting to the user. So, like I said, these scripts are being currently, as of making this video, are being evaluated by systems engineers on the TMT team. So results will follow. I hope you enjoyed this quick start. Please let me know if there are any questions via GitHub issues. I will be monitoring those, and as always, pull requests are are welcome. Thank you very much.